Hello students, I am Professor Dheeraj Kumar Singh from Department of Mechanical Engineering, Sagar Group of Institutions, Sistekar, Bhopal. Dear students, today we are going to discuss equivalence of Kelvin-Planck and Clausius statements. Before discussing this topic, I want to discuss and share some of the important points with you all that we have already discussed second law of thermodynamics, in which we have seen thermal energy reservoirs, Kelvin-Planck statement, Clausius statement, and the applications of Kelvin-Planck and Clausius statements like heat engine, refrigerator and pump. And we have seen the relationship between refrigerator and pump too, and we have derived the equations and efficiencies for heat engines also. So today we are going to discuss what is the relation between Kelvin-Planck and Clausius statement. Today the topic is equivalence of Kelvin-Planck and Clausius statement. That means what is the equivalence between them? Are they both are parallel statements, or is there any difference? So today we are going to discuss these things. So main focus is that if we violate one statement like Kelvin-Planck statement, then Clausius statement gets automatically violated. Or I would say, if I will violate Clausius statement, then Kelvin-Planck statement gets automatically violated. Then how it will happen? We are going to see it. So dear students, the topic is equivalence of Kelvin-Planck and Clausius statements. So at first sight, Kelvin-Planck and Clausius statements may appear to be unconnected. Obviously, because Kelvin-Planck tells us about heat engine and Clausius statement tells us about refrigerator, right? So we feel that these two have nothing to do with each other. But it can easily be shown that they are virtually two parallel statements of the second law of thermodynamics and are equivalent in all aspects. That means the truth is that Kelvin-Planck and Clausius statement is virtually parallel with each other. This is the main thing. That means the violation of one statement affects the other, and the violation of other affects the first one. So we are going to see this. The equivalence of two statements will be proved if it can be shown that the violation of one statement implies the violation of the second, and vice versa. The same thing which I have told you earlier, that if we will be able to show the violation of one statement, then obviously the second will violate it automatically, and vice versa. So dear students, now move to the point number 1. This is, let us consider a cyclic heat pump P. We can refer this figure. This is the figure, right? So let us consider a cyclic heat pump P which transfer heat from a low temperature reservoir T2 to a high temperature reservoir T1, right, with no other effect. That means a cyclic heat pump in which only temperature is getting transferred from lower temperature body to higher temperature body without any external input, right? So with no expenditure of work, violating Clausius statement in the given figure 1. So dear students, we can see here this figure. So we are seeing this is a cold reservoir at T2 and this is a hot reservoir at T1. That means this is our source and this is our sink, right? So both are thermal energy reservoirs. So we are seeing the condition of heat pump here, that we have supplied or we have extracted heat, right, Q1, right? So we are taking heat from the cold reservoir Q1 and we are taking that heat to the heat pump. And what heat pump is doing? Heat pump is rejecting heat Q1 also. Why it is rejecting the same amount of heat? Because work input is 0 here. So this is the case of Clausius statement. If you will remember, the Clausius statement was that it is impossible to construct a device operating on a cycle which transfers heat from lower temperature body to higher temperature body without any external input. So what is this? This is the violation of Clausius statement. Clausius has told us that it is impossible to transfer heat from lower temperature body to higher temperature body without any external input. So we have violated here Clausius statement, right? So now here we can see, let us assume a cyclic heat engine E. This is the cyclic heat engine E operating between the same thermal energy reservoirs. Obviously the thermal energy reservoir for heat pump is same as the heat engine. So producing W net in one cycle, So this heat engine is producing net work equal to Q1 minus Q2. Obviously the Q1 is the higher temperature, Q2 is the lower temperature. So W net will be, net work will be Q1 minus Q2. So the rate of working of the heat engine is such that it draws an amount of heat Q1 from the hot reservoir equal to that discharged by the heat pump. It is saying that this heat engine is drawing an equal amount of heat which has been rejected by the heat pump. That means heat engine draws that equal amount of heat, that is Q1, as input here in the heat engine. Here it is output from the heat pump. So we are using that output heat as input in heat engine, right? So it is written the rate of working of heat engine is such that it draws an amount of heat Q1 from the hot reservoir equal to that discharged by the heat pump. Now then the hot reservoir may be eliminated and the heat Q1 discharged by the heat pump is fed to the heat engine. So if we want the same amount of heat to the heat engine, then what is the need of this thermal reservoir? If this heat we want to supply, right, the same amount of heat if we want to supply to the as an input to the heat engine, then I think there is no need of this hot reservoir, because we can take that heat directly to the heat engine, right? So it is saying that if we are taking the same amount of heat which has been rejected by heat pump as an input to the heat engine, then there is no need of this thermal reservoir, or we can eliminate this thermal reservoir, right? So if we will eliminate this thermal reservoir, then what will happen? Then only one thermal reservoir will be there, right? There will be only one thermal reservoir, and that heat Q1 is coming here and it is producing net work after rejecting some amount of heat to the cold reservoir at T2 or the sink. So it is here written, so we see that the heat pump P and the heat engine E, right, acting together constitute a heat engine operating in cycles and producing net work while exchanging heat only with one body at a single fixed temperature. This violates the Kelvin-Planck statement. So dear students, what was the first case? First case was that we have violated the Clausius statement, right? How we have violated the Clausius statement? By not supplying any work input to the heat pump. Our Clausius statement violates. Then what we have done? The same amount of heat which has been rejected by heat pump, we have used that heat as an input to the heat engine. So there will be no need of this hot reservoir, this thermal energy reservoir. So we remove that thermal energy reservoir and we are taking that heat Q1 directly to as an input and in heat engine. And what we are getting finally? We are getting W net Q1 minus Q2, right? So net work we are getting here. But dear students, as we all know, our Kelvin-Planck statement states it is impossible to construct a device operating on a cycle which produces work continuously by exchanging heat with a single reservoir. That means Kelvin-Planck told us that if you want to produce net work, then you have to be there two thermal energy reservoirs. But here we can see that we are having only one thermal energy reservoir because we have removed that thermal energy reservoir. So in that case, our Kelvin-Planck statement gets violated. So we can see here that if we violated Clausius statement, then automatically our Kelvin-Planck statement got violated. Now dear students, we will see that how we have violated Kelvin-Planck statement, and because of that how Clausius statement gets automatically violated. So we can see the point number B, point number 2, this is the figure, right, in which we are showing that violation of Kelvin-Planck statement. So here we can see that Q2 is 0. So if Q2 is 0, that means our heat is not rejected to the this particular cold reservoir. So it is very obvious we are exchanging heat with only one single reservoir. So we have already got the case of PMM2. This is perpetual motion machine of second kind, right, in which our heat rejected is 0. If our heat rejected will be 0, then this is the case of PMM2, right, because and this is also the violation of Kelvin-Planck statement, because Kelvin-Planck told that if we want to produce network, then we have to exchange heat with two reservoirs, two thermal energy reservoirs. But here we can see that heat rejected is 0. That means it is not connected with any other thermal energy reservoir. So let us consider a PMM2, that is E, which produces, that is heat engine, which produces net work in a cycle by exchanging heat with only one thermal energy reservoir. This TER is thermal energy reservoir at T1, right, and thus violates Kelvin-Planck statement. So it is written here clearly that PMM2, which produces net work, this is W is net work, in a cycle by exchanging heat with only one thermal energy reservoir, that is hot reservoir at T1. So this heat engine is exchanging heat with only one thermal energy reservoir. So this will be the case of PMM2. That means we have already violated Kelvin-Planck statement, right. So now how we will get the violation of Clausius statement? Let us see further. So let us assume a cyclic heat pump P extracting heat Q2 from low temperature reservoir at T2. So this is heat pump P which is extracting heat Q2 from cold reservoir at T2. This is low temperature reservoir. So from low temperature reservoir our heat pump is extracting Q2 amount of heat, right, and discharging heat to a high temperature reservoir at T1, and discharging heat, right, and discharging heat at high temperature reservoir, right, at T2. Okay, so discharging heat to a high temperature reservoir at T1, this is T1, right, with the expenditure of work equal to what the PMM2 delivers in a complete cycle. So what it is saying, this is saying that is heat pump is extracting heat from a cold reservoir and sending heat to a high thermal reservoir by the help of that work input which we have got by the help of PMM2. So dear students, I want to tell you, if that PMM2 is not possible, if the PMM2 is not possible, then how can it will supply work input? So obviously if it is exchanging heat with single reservoir, then how it will produce work? If this is impossible, then that thing can also not possible, right? So here it is written delivers in a company. So here E and P together constitute a heat pump working in cycles and producing the sole effect of transferring heat from a lower temperature to a higher temperature body, thus violating the Clausius statement. So dear students, we can understand here by the help of these figures that if we have violated our Kelvin-Planck statement here, so automatically our Clausius statement got violated, because for the success of Clausius statement we should need a proper amount of work input, but this work input is not valid because it is the case of perpetual motion machine of second kind. So this case will be not valid. So we will treat it as that we have not got any work input. So if we have not got any work input, so how can we reject the heat at higher temperature? So that will be impossible, and that is the violation of Clausius statement. So by violating Kelvin-Planck statement, we can see the Clausius statement got automatically violated, right? Now dear students, we will discuss what is reversible process and what is irreversible process? We have already discussed some of the important points related to reversibility and irreversibility. So dear students, there are two things. The second law of thermodynamics enables us to divide all processes into the two classes. First is reversible or ideal process, and second is irreversible or natural process, right? So normally we perform our functions or our works in a reversible or ideal processes, right? So a reversible process is one which is performed in such a way that at the conclusion of the process, both the system and the surrounding may be restored to their initial states without producing any change in the rest of the universe, right? Means there should be no effect of the system on the surrounding and of the surrounding on the system. So a process is said to be a reversible process if, when reversed in direction, follows the same path as that of the forward path without leaving any effect on system and surroundings. So that kind of process is known as reversible process. This is very clear. Dear students, if we will talk about irreversible process, so a process which is not reversible is an irreversible process. So a process which is not reversible, no process, is known as an irreversible process, and it is due to the lack of equilibrium during the process or due to the involvement of dissipative effects. So why irreversible process or irreversibility occurs? It occurs due to the lack of equilibrium during the process or due to the involvement of dissipative effects. If we will talk about the lack of equilibrium, so how lack of equilibrium can come? So it comes normally because by the heat transfer through a finite temperature difference and by the lack of pressure equilibrium within the interior of the systems or between the system and surroundings, or in some cases irreversibility can be seen in free expansion processes also. And if we will talk about some dissipative forces or dissipative effects, then dissipative effects can be considered in the case of friction, in the case of paddle wheel work transfer, and in the case of transfer of electricity through a resistor. So that's all for today's class, dear students. In the next class we will discuss Carnot cycle. Thank you.